All right, so we talk about objects moving and figuring out how they move to try and describe that motion. One of the first things we need to talk about or decide on is how are we going to measure, right, the distance an object moves. And that usually requires that we start with its initial point, which we call, anybody know? Where it originates? The origin, right? We can put that origin anywhere we want. In this case, I'm going to put the origin right here where this car is, right? We start talking about that. So, for the sake of discussion today, this point of the desk will be the origin. Now, from here, we're going to be moving in only one dimension initially. So, like along the x-axis, not just like the coordinate x-axis you're used to, number line. So, to the right would be numbers that are positive or negative. And to the left would be numbers that are negative. Everybody good there? So we look at then, mathematically, what's the first sort of measurement we make or can make? The car moves from there to here. We can measure how far it's moved, correct? Now, in terms of how far it's moved, does it matter whether it's, in this case, I'm talking about distance, is there a positive or negative associated with that? If I just said the car's going to move 1.5 meters from the origin, or I'm going to move 1.5 meters from the origin, does it matter which direction I go for that to happen? No. I can go 1.5 meters this way, or 1.5 meters the other way, right? Is everybody good there? And if I looked at the time that it took me to do that, or if I looked at the time that it takes the car to move that 1.5 meters, what would I have if I mathematically compared that distance over time? What would we call that? Anybody know? Is it necessarily velocity? Ooh, acceleration, good terms. ACC, velocity. But what is that basic ratio of distance over time? Speed, right? Speed. So speed equals distance over time. Right? Mathematically, normally we see that as distance equals speed times time, which is sometimes referred to as like D street. Formally, you also have that, oh goodness gracious. Let me see if I can make this thing now. That triangle, distance, speed times time. All right, we're familiar with that one? Yes or no? We're familiar with that whole triangle concept with that? All right. So either one of those works. If the object, the cart moves from here 1.5 meters that way in 1 second, or if it moves 1.5 meters from here that way in the same amount of time. Is there a difference in the speed? If it goes 1.5 meters in 1 second, is there a difference in the speed? It's going left or right. Everybody agrees, yes, there is? No, there's not. There's not with speed, right? The fact that it's going 1.5 meters in 1.5 seconds, or if it went 2 meters and back, down to, up to, how much total distance has it covered? Down to, back to. How much total distance? Everybody agree 4 meters? And if I took the time, right, that I divide that out, I would get the same speed for the down and back, as well as the down and the back if I looked at them separately. Is everybody good there? So this speed really only involves how far I travel. Doesn't matter anything about a direction. Right? I could do the same thing if I were here and I set my cart here and went this way and back. Is everybody good? Speed, nothing to do with direction. There is a quantity that deals with direction. where direction has to be taken into account, who mentioned over here? Velocity. Where velocity is not distance over time, but rather a quantity we call change in position over time, or displacement, which is the difference between where I start and where I stop. Or my final position minus my initial position. X final. X naught, or you might see it as Xi for initial. Is everybody good there? This, the direction matters. Okay? If, for example, I'm here and I start at the origin, and I move in the positive direction, and stop right there. How far am I from where I started? Anybody? If it's 2 meters long. I'm plus 2 meters away, right? If I put my origin right here and went that way and stopped 2 meters away, how far am I from my origin now? Negative 2 meters, right? It's still 2 meters, but because I moved in the positive direction or the negative direction, it's important. Right? If I'm on a cliff and I want to move 5 meters from the cliff, does it matter which way I go if I'm standing on the edge? Because if I go 5 meters that way, I'm in trouble. Right? I'm falling, hoping I have a parachute. If I go 5 meters this way, I'm probably going to be fine. Direction is important. Okay? And most of the time, speed and velocity are used to mean the same thing in physics. Right? And they are the same thing, unless I change direction. Okay? Unless I change direction. If I change direction, then the distance I travel and my displacement will be different. The easiest example would be if I start here at 0 and I go down and back. Okay, let's say the track is 2 meters long. Okay, so I go down. And back. How much distance have I moved on my track total? 4 meters, right? What's the difference between where I started and where I stopped? 0, right? Is everybody good there? I started here, I ended up here. For velocity, I haven't gone anywhere. Right? That way I went plus 2 meters. This way I went negative 2 meters, so I've gone nowhere for velocity. And that would be the difference. My distance or speed would be 4 over that time. My velocity would be 0 minus 0 over that time. Where I started to where I stopped. Okay? Does everybody see the difference there? If I looked at my origin being, I guess we'll go here again. If I go plus 2 meters this way, turn around, and go 4 meters this way, how much distance have I covered? 2 plus 4 is 6, right? What about velocity or displacement? I've gone negative 2, right? Negative 4, right? Or negative 2 plus 0. Started to stop. Is everybody good there? So my displacement, negative 2, even though I went 2 and 4, 6 on the ground. Okay, and that's really the difference between distance and velocity. Right? Now, graphically, I guess first of all, if we look at this object, when I let it go, is it going once the little spring lets go, is it traveling the same distance every second or every interval of time, do you think? Try it again. Yes or no? Pretty close? How can you tell maybe it's not quite the same? How could you tell that? Could you tell by looking, or could you tell by hearing?
The sound.
Did it sound a little different, right? So think about just the part where it goes from here until it hits there. Pretty much constant? So if that's the case, if I wanted to make a graph of the position versus time. Position versus time? Yes. What would that graph look like, do you think? It's going the same amount of distance every 1/10 of a second. What do you think that graph would look like? Could we come up with a way to figure out what the graph would look like? Let's say each of those is 1/10 of a second. Each one of those, 1/10 of a meter. So if it's going 1/10 of a meter every second, does it make sense that the graph would look like that? Let's see if in fact it does. I have here a computer that's hooked up to it's got a motion detector. It's got a motion detector down here that measures how far this thing is from it, like 30 times a second. And as it goes down there, it'll plot that graph. As it shows up, you'll see how it works, right? And you'll see if we're in the ballpark here. Now, so once I started it and pulled the pin, what happens? It's a straight line, right? Can I get a better look at it? What was that, from about 1/2 second to 2.5 seconds? So the Y scale. Oh, what happened? Oh, I messed myself up there. And time. Now, so during this time right here, does it look like, in fact, yes, it's going the same amount every time? Except for what happened right here? Slow down. All right. The spring on the end of this started slowly slowing it down and then shot it back, right? Is everybody good there? But during that initial time, right, my position time graph, when I'm going at constant velocity, is a straight line. You need to make a note of that, right? The graph, because we're going to look at the graphs of position and time, right, as well as velocity and time, and acceleration time. And we'll talk about what acceleration means in just a minute. Does anybody have questions here so far?
So what you just told us to recognize
for the position time graph, position versus time, x versus t. Right? And there's really two choices for motion. There's constant velocity and accelerated motion. Does that make sense, L'Oreal? This case, constant or changing the velocity or the speed. It's constant, right? It's a flat track. Does that make sense? Once I let the spring go, it just keeps going. Right? Nothing's there to make it change. So a constant velocity, it should go the same amount of time every interval of time, and we should get a straight line. What about velocity or speed? Are they the same thing here? From there until it hits here? Same or different? Velocity, speed. Same thing, right? Until I change direction, they're the same thing. Well, if I look at that graph of velocity versus time, I see basically what's happening right here. Basically the same, right? Between 0.65 and 0.67. Is everybody good? Basically flat. I could probably get a better run at that if I wanted to. But basically constant. And you can see that it did slow a little bit. It started off a little bit slow and then got a little bit slower as it got down here. If I made it initially a little bit farther, then I compress the spring so it beats a little bit more rapidly. Let's have a little run here. And I'm only going to look at the time it goes down and back, or just down. Try one more. You're right, we should be able to tell, correct? So here we're at like 0.8, 0.9, so pretty much constant. So really good there. And if I made that graph, expanded that, it would be much flatter. So constant velocity, or speed versus time, right? For constant case, should be a flat line. So position versus time, velocity or speed versus time should be like that. Now, the other term that we have to deal with is acceleration. Does anybody know what acceleration is? By definition, what does it mean if I'm accelerating? Changing your speed, right? Going faster if I'm sitting in a traffic light and take off, right? If I'm coming to the red light, slowing down, am I accelerating? I'm slowing down, right? I'm accelerating negatively or slowing down, but all acceleration is a change in velocity or change in speed. Like for us, change in speed, change in velocity is more important, over time. Right, that equals acceleration. Change in velocity is the same thing as v final minus v initial over time. And this, something you also want to copy down, like the definition of acceleration. VF minus V naught over T. Is there a more common expression of that? Is anybody familiar with it? A way it's usually written in a different fashion? If I just do some algebra, multiply both sides by T, and move some stuff around, I get VF equals V naught, or the initial, plus A times T. It's the same formula, except this one looks more like a formula, an algebra equation that we might be used to, rather than that algebra equation with a fraction, which we all hate, right? Okay? This is an important question you need to know. Delta x over t, right, is equal to velocity average velocity at constant velocity. There's a different formula to calculate average velocity if we are changing velocities. Okay, so we talked about velocity, or sorry, distance. We look at the velocity. And the third one we could look at, what do we think the acceleration would look like in this case, where we're just moving down and back once the spring lets go? What do we think? Is it getting faster than slower? Or if I'm just talking about going from here to here, once the spring's done, or let's say from there to there, is it changing? Not measurably. So what should my acceleration be? A flat line, right? 0. Does that make sense? And pretty much from here to there, it is. What did I do wrong? Oh, I should probably use the other. This one right there. See right here, E much 0. Is everybody good there? So my acceleration time graph should be 0. So everybody good with that? Any questions there? All right. What happens if I start my cart here? And I'll let this be the origin. If this is my origin, which direction is it going to move? In the negative direction, right? And what would my position time graph then look like? Here I can look at all three of them real quick. What should my position graph look like here? It's going to be a line going Up or down? Right? In the negative direction, right? So it should have a negative slope. And it should start where? Should start up here, correct? Yes or no? Everybody good with that? What if I put my origin over here? What if I started at the origin but went in the negative direction? What would that graph look like? Anybody? I'm at the origin going in the negative direction. Go what? In the second quadrant? Or the fourth quadrant? What do you think? It's starting at 0 and going negative, right? And this is my position. So this would be where it's going to the right, and this would be where it's going to the left, correct? So you think it should go that way. Straight line? Maybe I can get it to go. Why? Oh, just let me be in the negative. Because now it's positive that way. It's not to be over there. Questions there? Everybody know why that one didn't work? Because wherever this is where the origin is. So it's pointing in the negative. It's pointing positive from this, regardless of what I try to call it. Right? This thing points positively wherever it is. So I can say that's negative, but to this it's positive. All right, so we're good there. And notice my accelerations or my velocities are constant. What happened here? What if I let it go down and back? If I let it go down and hit and come back. All right, my acceleration, notice what happened right here. Acceleration 0, what happened here? That's where it collided with the ramp and then it came back at 0. What about my velocity here? Went from here to 0 while it was against the ramp, then to negative. All right, so everybody good there? Position went up. This is where it's compressing the spring and then starting to come back. So everybody good there? All right, then the last little part of what we'll talk about here on our graphs, if I take the slope of this graph, I would get distance over time, right? What is distance over time? Speed or velocity, right? If this is position, then that would be velocity. So the slope of this makes velocity. And what's the slope of the velocity graph? Velocity over time is equal to what? Acceleration, right? So those three graphs are related to each other through their slope. The slope of position time equals velocity. The slope of velocity time equals acceleration. Is everybody good there? Okay. Now, we're going to then change things up a little bit and look at what happens if we're dealing with motion that is accelerated. Okay, motion that's accelerated. Does everybody understand how this case is going to be different than the one we just had?
Yes.
All right. So here, I'm just going to have a cart. I'm going to let it roll down the hill. Okay? Do you think that the distance it covers every second, or every part of the second, will be the same here as it was on the flat track? Will it cover the same amount of distance every interval? Why not?
I think it'll cover more.
As I get farther and farther along, it'll cover increasingly more? Is that what you're saying?
Yeah, because it will accelerate faster.
Right, because it's accelerating, not faster, it's accelerating at all, because the last one didn't, right? Last one slowed down a little bit by friction, maybe. But this case, as I go, it should get faster and faster and faster. And if it gets faster and faster, that means that the amount of position that it changes every time, right, should be greater than the increment before. If I go a tenth of a meter this time in half a second, the next half a second I should go farther than that. And the half second after that I should go farther than the one I went before. Right? And what would that graph then look like? We'll set it back there. Nice. X versus t for accelerated motion should be a little bit farther each time, and it should look parabolic or exponential. Let's see if in fact it does. So just looking at the first graph. Now, obviously, we go from so here's where I started the timer. Here's where I let it go. And does that in fact look parabolic? Yes or no? Is everybody good there? Now, can I take the slope of a parabola? Can be done, but let's not go crazy, right? How can we do it? Well, we don't have a line though. We have a curve. Anybody know how to take the slope of a curve? I can take a tangent to it, right? But you actually have to know what this function looks like. What ax squared plus bx plus c it is, and then you take what's called the derivative. Fortunately for y'all, we don't get to do that here in honors physics. Right? We're just going to go with, it's a parabola, and we're not going to deal with how to find anything out of there. Okay? However, if I look at the way, if the position over time, if delta x1 over t1 is x, and delta x2 over t2 is a bigger x, and a bigger x, what should that say for my velocity? Is my velocity getting faster and faster and faster as I go? Staying the same as I go? Or somehow incredibly slowing down as I go? It's getting faster and faster, right? And if I slip that velocity graph back up there, oh, I guess I have to go down here. And if I then change this time scale on this too. What's my velocity when I let it go? Is that a straight line? Getting faster and faster and faster as time goes on. And what about over here? My acceleration from when I let it go down the ramp. It's accelerating the same amount, right? Why? Does the ramp change? During this thing, the ramp is constant, right? So the amount that is pulled down the ramp is constant. The amount it changes by that pull should be constant. Is everybody good with that? Now, the only thing, or not the only thing, but one thing we need to look at then is the average velocity it has as it goes down that ramp. What velocity did it have here when I started it? When I let it go, was it moving? When I took my hand off, what was its velocity? 0, right? And do I have any idea how fast it was going down there? Right before it hit. Could I find it? If I looked right here, for example, could I say that that's like 1.7? Does everybody agree with that? Okay. Now, forget the velocity thing. If I told you you had 2 grades going into your grade, one was a 90, one was an 80, how would you average them? 90 plus 80 over 2, right? I can do the same thing with my velocity when I'm accelerating. My VF 1.7 plus 0 over 2, or VF plus V naught over 2 should give me that average velocity. In this case, 0.85. That's different than the average velocity we talked about when I'm at constant. Delta x over t is for constant velocity. This is V average when I'm accelerating. You need to know the difference between those two cases. When we're accelerating, right, we're going to be falling down a hill. We'll be told we're accelerating. We'll be rolling down a ramp. falling through the air, right? Those kind of things. Much more prevalent than I'm going to drive or go along a flat path at the same rate all the time. It's kind of boring. Right? Not a lot in the real world does that. Right? Is everybody good there? Now, you have then that page of notes. You should be able to deal with most of those blanks, fill those out, handle those. Then there's a few problems right here. And I'll write the formulas right up on the board that we might need to deal with. And you need to realize that some of those formulas, they're up there in blue as well. Those formulas that are up there in blue, a couple of them are definitions, right? Primarily df equals v naught plus at. That's a definition of acceleration, right? And then average velocity equals change in position over time is that average velocity when we're not accelerating. Those other two up there, x equals x naught plus v naught t plus 1/2 at squared, is derived, as well as this one is derived from this equation and that equation by substitution. We're not going to go into how they come to be. Realize those four formulas plus this one are things you need to be familiar with. Write this one down, make sure you have it. You can copy those down. And then try and give a little work on some of these problems. The first A10 through A15. No, hold up, back up, mister. On the back of this page 1, there's a few little problems that we'll look at. And we'll talk about some problems tomorrow and continue where we are right now.